Jeez, I got it. Okay. You've been replaced.
Okay, last day of class. And, just as we did on the first day, where we got the mechanics, classical arrangements, and all that by taking two balls and running them into each other, or taking two lightning to running them into each other. It's amazing how much information you get from running things into each other. It's kind of a childish thing. It's, if you have two bugs, let's see if they'll fight. And that's the biological analog of what we're doing here. So today I would like to begin this, but I'd like to take an example that is very similar to the one that will be the final exam. It will be a blank piece of graph paper like the one that I've given you with maybe some extra clues here and there, but mostly blank. And I'd like to show an example. It's just slightly different from the one that we did before. Now, the one we did before is on the board here, and before we go any further, I want to make sure that you understand how to build a hyperbola using the Thales geometry, and that's a very key thing for. Let's see if I can find the compass here. There's a compass here. That's what I'm looking for. So the basic idea of don't need it. I'm just going to symbolically use it here. Basic idea of this particular circle right here that goes with a radius equal to the ordinate of the phase vector. That circle, you definitely want to add that to the graph if you haven't already. And the basic idea is that it goes through the lowest point in the frequency, call it a dispersion relation. The matter wave dispersion relation is this green curve that I've sketched in here. And the construction of that curve is obtained very simply by picking a x value randomly, extending your compass to the 600 terahertz tick mark, and then making a little dashed mark or dot or something to indicate a point on the hyperbola. So for example, these points that you see here are the other side of that dispersion function, that mass shell as it's called. For example, if I were to want to get whatever point that lies above that value of the horizontal coordinate, I simply take my compass and as accurately as possible put the marker in the center of the 600 terahertz tick line, and then just bring it up to the point where it's above that particular line, which is right there. Okay, so there's a mark there, and then it's just a matter of carefully drawing a line that goes through those points, and I'm attempting to do this just by hand here, but that's this magic curve that we're after for this, and then it goes is very tangent to this point right there, and then continues on its way, and is tangent to this line right here, which is one of the first lines that we drew. This vector right here was the difference between half the difference between these two vectors, the ultraviolet 1200 terahertz laser line and the infrared 300 terahertz laser line right here. Half the sum of those vectors is basically what we're making with this one and this one right here. That, I'm sorry, this one right here. That's the 600 terahertz laser before we tuned it up, doubled its frequency to make the ultraviolet beam. So, the geometry that we're making here for the per space-time, and very easily copied parts of it to make the space-time Minkowski graph that we've looked at a little bit. Anyway, that geometry for both of them is right here. A little bit more than we need. So that particular B circle, the bottom of the hyperbola, I guess is the way to think of the B, the base of this light, the point where the coordinate system that the light makes stops moving. As far as you can see, that is the group part of it stops moving. The standing wave becomes a standing wave right here. Everywhere else it's a movie thing like we've seen in the movies or the animations that we've shown. So what I'd like to do is just go ahead real quickly. First of all, review a couple of things that we talked about, and a lot of links here that take you afield. I won't pause on those right now. But anyway, what we've been doing is taking the standing wave situation where two lights of the same frequency meet each other, same frequency and same amplitude. We'll talk about the amplitude later if you're interested. That's a really neat thing that happens. But having tuned up the laser on one side to double and tuning down the one on the other side, this one kind of wins and makes something that leans in that direction. There's the right-hand laser vector that's double what it used to be, which was right about there. That was first base before. Now first base is a marathon, as I said before. But the second base line and then the third base to home, because baseball terminology, are much shorter. They're half as long as they used to be. So what we need to get a feeling for is how this graph folds from the nice standing wave that we started with. And all of this geometry is inside either space-time, or we're most interested in per space-time for making a case for a derivation of quantum phenomena, quantum functions in a relativistic regime. So there's quite a bit of things that we're doing here to carry this forward. So I'm going to go ahead and point out a couple of other things that are happening here. And I think it would be a good idea, probably, if I got these screens synchronized a little bit. One of the things that I definitely want to do is take a quick close-up look at this crazy wave when it's doing this dance that makes a coordinate system, Lorentz coordinate system in this case. And I want to point out very quickly, and this is in space-time now, this other stuff is in per space time, the frequency versus wave number. That is this graph that I think you should all have a copy of this, and if you want more, they'll be available online. In this lecture, this is just a page out of this particular lecture. Okay, so what I want to do is go through this one, but this one is a little different in the sense that now, instead of having immediately a thing that's twice as big as what we started with, and something that's half as big, this one, and we're going to keep the same, but we're going to take this one over to 2.5. So this one is going to have 1, 2, 3, 4, 5 times the frequency of this one. 5 times the wave number and also 5 times the frequency. And of course, the wave number, the horizontal component, has a negative sign for this one and a positive sign for this. So we're following the baseball rules. You cannot run outside of the baseline, right? Well, light can't either. Light has to stay on this 45-degree line or on this one to operate in this plane. But that 90-degree angle, that right angle coordinate system, say x versus y, is an important one in the sense that it is carrying a hyperbola that goes somewhere, and we got to find out where that is, because in this case, this thing isn't quite the inverse of this thing. That is, it's true that the exponential function's in there, inverted here, but we need a scale. We got to rescale our coordinate system in order to actually get the frequencies that are operable here. So this is a way to do, and still keep nice fractional numbers to play with in the arithmetic that goes behind this. So basic idea here is that red shift factor, blue shift factor cancels out to give you this base. The base will not necessarily be here. In this case, it will not be. It will be a little bit higher. We'll see what that is. It's about it was 5/4, and the square root of this is the b constant. That's where it's going to be when we get done with this construction. We're going to have something going through just a little bit higher than 1, 1.12. So it's close to being the same scale, but it's not the same scale. So that's what we need to do before we get into the quantum mechanics. I wanted to see that simply to get one more chance to play with the thing that we're going to be doing in the final exam. The graph that you're going to be making is going to involve this kind of graph paper here. Okay, now when it comes to looking at space-time, be aware that there are two kinds of lines running through here. These guys going faster than light, the speed 5/3. That's the I'm sorry, the inverse of the group velocity, which is the phase velocity in units of c. That 5/3 c is represented by these blue lines going through. Used to be infinitely fast. It used to be a flat in the case of the standing wave, but now they're just really fast, faster than light. And the other side of the story is the group velocity, which here is 3 units this way for 5 units of time. So all of these green lines represent the group that makes the time axes, the time grid of the Minkowski plot, whereas the fast guys, the phase, always faster than light, is making the horizontal, more horizontal lines of these, what used to be squares are now rhombuses. So just for that, just to say that one more time, for the geometry, this is going to also have a little bit of a twist. Okay, let's see if there's anything else we need to say here. Here we're just spelling out how these numbers come. That is 0.8, 4/5 that we're seeing for the distance between those, and then this one's 1 4/3, 1 1/3 going there, and let's see if there's anything. Yeah, these are what we're counting off here is 1.1, 1.2, 1.3, 1.33, 1.4, 1.5. So the ticks here are kind of doubling from the precision that you have in the graphs that you're using. But anyway, these two numbers then show up again up here. The thing is symmetric around the 45-degree light cone, if you want to call that this thing as it swings out and goes around and makes a cone that everybody talks about in relativity. Okay, now the circles that we're going to be playing with, there's some shown here. I don't need to talk about that now. We'll see it, but they're going to be segments on this graph that we need to label with hyperbolic functions and circular functions. That's that business that we talked about before, where you have, for every hyperbolic function, like the hyperbolic tangent is really important. That's the one that's giving you the group velocity and classical velocity. The inverse of that is the phase velocity, which has been hidden from us and continues to be hidden. It's very difficult to see the phase velocity in any quantum mechanical, certainly, but also in coherent optics. The phase is very difficult to measure. In any case, those two are the inverse of each other. These two are inverses of each other. This one's an important one that we've already talked a little bit about. This one right here being Einstein time dilation, and the inverse of this one being the Lorentz contraction. So all of these, all of this simple trigonometry lesson that's behind this is has got some physics attached to it, both in per space-time, that's what we're going to talk about today, but also in space-time, which we talked a little bit about last time. Okay, let me take this one ahead a little bit and get up to a point where we're going to begin today, and that's this graph right here. So we'll use this as a reference for the names that go on them, the trigonometric names, and they come in pairs. But one of the first things that I would recommend you do to get this thing started and to get the main parts of it is to do the half sum of these two geometrically. And while you're at it, you might as well draw another rectangle down this way and do the half difference. So this guy right here is R minus L. That's this big R here minus L. Okay, minus the L vector, which is right here. And right here is the actual coordinates for it in this particular scaling, which is not the scaling that we actually need, but we're going to go ahead and use it because it has the numbers that we can easily identify without looking at decimals. So this particular thing is kind of interesting because the opposite of this R here, is the sum of these two. Okay, not half the sum, just the sum. And this is very much like the group projection stuff we talked about before. You had the projection that was written as a sum of idempotents, and then the idempotents themselves were a bilaterally symmetric thing, half, either the sum half difference or the half sum. Now, putting that back again, this thing is just the sum, and this thing right here is either plus or minus the difference of these two right here. So there's the difference right across that diagonal, perpendicular to the main diagonal, which is the sum. Okay, so don't let that little very simple geometry get away from you. That we need that. Okay, now pretty much what we have on the board there, and then there's an important circle. So this is one that you ought to put on the graph that is involving the half speed. I'm sorry, it involves the 600 terahertz problem with 1200 and 300 terahertz. So on this one right here, what I'm interested in is the circle that we get right here. And we're looking at a point on a hyperbola, And this particular one, of course, starts there, but you might as well go finish it all the way to the end. And notice what it does because of that, this thing being a half sum. It should end on the high frequency of the high frequency component and begin over here on the low frequency component. So 300 terahertz, that should come right through this. And so that's the arithmetic mean of the, well, 4 and 1, the square root of the product of the two, the high and the low frequencies. Okay, so that, from this particular example, is done the same way. I simply know where the end of the vector is. I draw a circle, and it goes through, and this is important, it goes through not an integer point, it goes through this number right here. So there it is, 1.12, if you could read 3 figures, and it's hard to do that with any of the graphs that we're using, but you can see that it's in the right neighborhood for that. Okay, so that's one part of this. Here it goes right through the number that is the geometrical mean. This one's a number multiplied by a scale factor. So, okay, the next step on this, let me keep up down here because some of this stuff is...
Dr. Hart?
Yes.
I have a question. What is that B? What does it mean?
Okay. Basically bottom. I mean, this hyperbola has a minimum, which imagines going down and ending up at the bottom. Yeah. Okay. It's also the base. It's the base frequency. It's the frequency that represents the rest frame of the light.
Okay.
Right. If you've got two colors coming, one say a high color and a low color coming at you. Remember that sort of weird thing we talked about, right? And the question is, how do you find a frequency that it would have if you got going into that frame? There is the rest frame of that pile of light.
Okay. And that's what that B is. So, okay.
Yeah, I picked it because it's basically bottom, okay, or base. Okay. Does that make sense to anybody else have a question about that? That's very important. Now, this is another circle that's important. Wherever that goes through, draw another circle. Okay, we didn't do that way because we kind of already knew the answer for this one, but this one is a little trickier. In order to keep these fractions and things, I have to do this with scale factor. Okay, let's see if I'm not up to speed down there. There's the actual circle, and then for the phase, and then there's a circle for the base. The lowest, the smallest circle that we're going to get touching the hyperbola that eventually we make out of this. Okay, let's see if, next thing. Now this is weird. If we've got a circle for the hyperbolic cosine, which is this component right here, the half sum of the two exponentials, we'd like to have the half difference represented by a length as well. The hyperbolic sine is the other component right here. In this particular structure right here, it just adds up to 1. Over here, it was a different number that we got for that, the hyperbolic sine for this component right here, the radius of this circle, the hyperbolic sine circle, this guy right here, we're talking about something that has a radius of 3/4 in these units. That's if I get the right coefficients, but the actual hyperbolic sine for this thing is 0.75 in these units, where this is the unit. It's actually sitting here around 1.5. It's half of that because this is a 2 for the this particular coordinate system. But it might be nice if we just called that 1 and then work with the scale factor that this thing has, which is 2. But in any case, that part of the thing is a circle that has that hyperbolic sine radius and intersects the base circle, right there. And that's the point through which you draw the angle that determines the k vector of this pack of light in a waveguide. Pointed that out really quickly last time. We'll look at it more closely later. In any case, that's a line that you definitely want to have as part of your graph if you're going to do a complete connection here with both the trigonometric hyperbolic and the trigonometry circular, the circular part of it. The circular part is the one that goes with the Lagrangian. So I'm using a sort of a yellow color here, but I'm coming up here with a line, and that line, you should put the ruler so that you actually make a tangent contact to the circle at that intersection. And so this right here, going off to infinity, that is the waveguide deviation angle is what it is for our people working in a laser or fiber optics lab. But for astronomers, this is very important. A measure of a light beam that's going transverse to your motion, transversely. So this vector right here, and I call it stellar aberration angle, and I'll just go ahead and draw a little star here that appears to be over here. I'm going so fast in this direction that the light, in order to go down my telescope, has to go at an angle because I'm a significant fraction of the speed of light here, 3/5 in this case. So the light just comes from that star, and as my telescope moves by, it goes down that line. So this is not trivial, but it's very simple on the geometrical part of this. And there's something else here that needs also to be done, and that is a tangent going this way is perpendicular to that. So this is an actual wavefront representation for the light coming or going to the star that was originally stationary in my rest frame before I started moving here, and now I'm moving here, and all the stars in the sky, as you move really fast in that direction, they all get dragged from behind you to in front of you. That's the magic that occurs when you could go really, really fast and look at the stars. And not only that, as they start to get high angles like this, they start to shift up in frequency. But their component in this direction, I'm talking in space and time now, this same graph works in space and time, the idea of that light is as it starts to get an appreciable stellar angle, it also starts to blue shift. So if you go really, really, really fast, you could take all the visible light that you could see and put it in a small cone in front of you and have it, well, be gamma radiation. I mean, it would really pick up its frequency as it starts to move in front of you. Not recommended, but fortunately we don't have anything that goes that fast. But there's lots of other things in the universe that are going very fast, and they're seeing that, if they can see. So that little twist to this geometry is kind of neat, because what it represents is a tangent vector to the k tangency point. That is, if I take my ruler now and go to the center of this circle that holds the hyperbolic sine function length, and put my ruler just below that so it's the width of a piece of chalk, and then draw, and I'll use the same color for the stellar aberration, sort of a gold or orange. Okay, the basic idea is that this is going to come through there, and it should be just tangent at this point, where this contacted the circle, this one contacts the base circle. So I'm going to try to do that, try to get that right. Now it misses that, but it should be very much, there's a point right there where it should be contact. And then it continues down here to intersect the axis at some point. So what we're looking at in the arithmetic, or the trigonometry lesson, okay, is this radius right here comes down. It's the same radius as part of that circle right there. And then the inverse function, because she is sitting on this side of that one. We're not going to bother with that one right now. We'll mention it at the very end. That's the thing that gives you the de Broglie wavelength of this matter wave. Okay. All right. So that needed to be drawn. Now, once this thing is contacting, it comes back here. If you want to make a fuss about where contacts have significance that's beyond just their own thing, is that contact point right there is pointing at. That is, there's a horizontal line that goes from that contact point to the other tangent that exists here, the tangent that is going to be the tangent of the hyperbola. So we go ahead and draw that just for the fun of it. Okay. That's this line that's shown from the contact point here to that. Now both this line and one that's above it that contacts the base circle, they're both the hyperbolic tangent. They're the ones that actually indicate the group velocity, the classical velocity of whatever this matter wave is, the group velocity of the waveguide, if we're talking about a matter wave that's been confined to a guide of either cylindrical or square with transverse electromagnetic, TEM mode, you could say. So that is this line up here, okay, and that I'm going to make sure I draw it in the right place. That one connects, if I'm not mistaken, with the stellar aberration line, and it connects where those intersect. So I'll go ahead and draw that one, just for the sake of argument here. Okay, where that connects, which would be right about there. Okay, there's the connection right there with the hyperbolic cosine line and the base point. All right, it's just parallel to this one, but a little bit longer. This one is hyperbolic sine long, just like that. Okay. And then this one right here is the same as this one, so there's another vertical line that you should put in there to indicate that. And this is making one of those zigzags. Remember when we talked about making geometrical sequences or series? That's what this comes. And then there's another one right there. So zigzag, zigzag, and you could keep doing this each time you're taking a factor of inverse hyperbolic cosine. That's the constant ratio that is being held. And this little gadget right here is what I call the Occam razor. Sword. The big Occam razor. Okay, this is the thing that sort of codifies all of the structure that we're drawing, and you can see it in the diagram of a waveguide mode. We sketched that before. Okay, that's pretty much it. There's other things that we can talk about here that make this really beautiful, and it's one of those things which I keep staring. I keep seeing connections over and over again each time I look at one of these graphs that are made this way. And then this is a table. I'm going to be asking you to fill a couple of pieces of a table like that in the exam. this is the actual simulation of what we just did. This one has a 5 out to here, and this one remains at 1. You just, when you play with this on the animation, you can just click on those points and change the vector. It will go since it is. Let's see if I've got the. I should probably go ahead and get this thing up to the point where we can see that. But I think I probably have forgotten to put a link to that. When we get going here, I will bring that up in time. Now, this is just out of Figure 11 in the relativity text. It's actually Figure 4 in Chapter 0, the shortened version of the relativity text. Okay, so there are the numbers showing the group and the phase lines going through space-time, making the same geometry over and over again, I might add. This thing sort of just does it once, and then you get the whole crystal in space-time from what I already called the keyboard of the gods. We've pushed these two buttons, I'm sorry, these two buttons right here give us, if you turn on the music, so to speak, all of that. And of course, this is just mirroring the geometry that is present there. Okay, so how can we turn this stuff into something that tells you about the functionality of quantum mechanics? That's the next step here. So basically the derivation. This is something that I've had several Nobel Prize winners come to this room, and I've asked them, do you believe that with a ruler and compass I can derive both relativity and quantum mechanics? And the one I remember the most was Stephen Chu. I gave him a piece of paper and said, put down the probability that you think that would be done. And he just wrote a big 0. Just, no way. And halfway through I was showing this, and that was only about 5 or 10 minutes later, he was literally sitting there looking at one of the animations, and he was sweating. It was like all of a sudden he realized there was this funny road around everything he'd learned. And then when he came back, he just wrote really amazing pedagogy. That was his comment. Okay, so, and he was right to just say pedagogy because it's going to take a long time before this thing gets to the point where it yields something completely new. That's what we keep working on it for. Okay, so it's answering questions, but it's asking them too. And that's, I think, a sign of a good theory, is that it does both. Okay, so here is this table, but now I'd like to point out a couple of things about it that has to do with the mechanics. And this time we'll be talking about phase and kappa phase with something that allows us to make dimensional changes. This thing has a definite number of dimensions. This is inverse time, C kappa phase. That's also inverse time. So I need some kind of thing, at least, it could be 1, but I need something to give me some units, because this is dimensionless. Hyperbolic cosine, hyperbolic sine, dimensionless. So I've got to have that B there. First of all, to do problems that aren't balanced quite as nicely as that one, but mainly here to get the physics into this geometry. Okay, and I'm going to just take the first power series term, the linear term of a hyperbolic sine. So we have a wiggly equal signs here, which means this is really a good approximation for U, so much less than C that it's pathetic. That's what we work with in our classical world. But we don't realize that inside every part of us and everything we touch, our things are going very relativistic. Now, just the electronic orbitals of hydrogen are already up to 137th of the speed of light. That's called the fine structure constant. So it's already relativistic just to the hydrogen that you have a lot of. You've got 2 of those things in every water molecule, right? So there's relativity going on, certainly in that case, but then you get down into nuclear, and man, there's just crazy relativity going on there. It's just mad inside the nucleus. Okay, so there's all this stuff that we're going to try to describe in more detail than you're used to. So taking the series, I get that. All right, and let's keep these things in sync. That means I have to get this thing synced up so that we do it. And then we'll, on this one right here, I'm going to back up because we're either going to use this graph or this one. So we'll be oscillating between these two as we discuss the functions that we've already tabulated from this geometry. Okay, so for the moment I'll just have you look at both per spacetime and spacetime. Okay, so that's just two entries pared down for sub-relativistic speeds of this table. Okay. Now, next stop, which is shown up there, and now I show it here. I want you to notice, and this is something, you know, stumble on sort of realizing that this is the way to go. This thing right here is something kind of like kinetic energy that we derived in a second or third session with this class. And while we're at it, of course, we were dealing also with things that we call kinetic energy and kinetic momentum. Okay, in fact, we started with this stuff right here, and then we derived this stuff here, right, using quadratic forms, right? That was basically the mathematics that was involved in doing that, okay? But we're noticing here that these two quantities, the frequency of the phase and the kappa of the phase, and we're talking about that phase, that thing that Newton just really couldn't believe was there in light, let alone matter. He absolutely didn't think matter would ever have this, but light, he agreed that light went crazy sometimes, and that's when it started to interfere, and that's what all of this is that we're doing here, is interference of colliding light beams. So this is where this takes a weird turn, and the basic idea is that I'm going to do here is, well, I got to match those units. I'm going to put a factor h just to get the right unit. So this is the right unit. So that this thing here, this is per seconds right now. I'm going to get an h onto that, and that has the units of joule seconds. So we're on our way, so to speak, actually joules for the energy. And this one over here has its units. Momentum needs to be varied. Does it need a different sort of thing? Well, no, it doesn't. hb over c squared works for both of them, both the quadratic thing and the linear in use. So momentum is appearing to be something to do with the kappa of the phase, and the frequency is appearing to have to do something with this scale factor times the frequency of the phase. Okay, so that's kind of interesting thing. Let me get it going on the other screen here. It's this clicker here. I can tend to forget those. And this is this if you haven't seen it, what's coming here already. This is where you get the bottom of the hyperbola being this thing, if you scale it up. So that's what, to solve this equation right here, there is perhaps the most famous physics equation of all times. It's written everywhere, from bridges to walls to, you find it in the John, every once in a while if you go to a place like Harvard or MIT, okay, or here. I've seen it here, actually. So the idea that that is some kind of energy that we're really interested in, and it's the bottom of the hyperbola. That bears some looking at, okay? Don't look at it with that one, but I'm going to go ahead here and ask at this point, is this just a lucky coincidence? When Stephen first saw this, he says, oh, that's just, you know, you're lucky. He didn't say cheap trick, but that's what he was thinking, I think. Okay. So far, it looks like a cheap trick. Okay. But you see, we haven't used the exact expressions yet for these two quantities. Now we're going to crank up the speed where we need that, and if you crank up the speed to that point, oops, I keep hitting the wrong thing here. That's going to make things happen. Okay, so this is, after you use the old-fashioned notation, is just the very famous equation. Not as quite as famous as mc squared, but it's got mc squared in it. That you can see by just using the old-fashioned notation for hyperbolic cosine. Okay. So here we go. We're not just getting Einstein's formula, we're getting Planck's hypotheses. The one that he thought was crazy. How can you associate energy with a linear, something that's linear in frequency? So it kind of looks a little bit, harried there. Well, he's unharried actually, but this is his a younger picture. Okay, very harried, right? After he came back from the Solvay conference, having made a big splash by getting the Planck distribution to fit experimental results by assuming that the energy of the light was given by a constant times a frequency, but actually it was a constant times n times the frequency. This is his hypothesis right here, that you would equate the total energy of that cavity to something that is a product of the amount of light in quanta, and they hadn't given the thing a name yet, they hadn't given it a photon name, and the frequency here. So these are both frequencies. This is just going to be the count frequency. When you actually go to look at that light and drain it, this is going to be the color of the light. This is the quality of the light. This is the quantity of the light, you see. A product of those two things that are per seconds gives you per second squared, and then this little guy h here that we put in here to fix our units finally gives you the right value, both in terms of the metrology, but also quantitatively. So that, I think, is an important part of this. I keep hitting this one. Okay. Now, this also motivates the whole idea of, in quantum mechanics, of normalization. So, if you think of the psi as an electric field, which we have been doing without saying it too much all along here, if you do have that, and have this as an energy density, or you can make it a flux, you can do it that way too. That this would be an integral over a cross-section, but this is the volume integral you're used to in quantum mechanics, and the psi has, this is called the quantum field constant right here, and that's the electric field you're used to in E and M. So that's the step here, is that this wave that we talk about for things, and we talk about it for matter as well, but this is light behaving like it's matter in a box. Okay. Now, as I say, big worry, oscillator energy quadratic in frequency. Yes, it is. We've made that point many times in this class. But if you use the right kinds of A's and everything, the resolution, and I say it's a dirty secret, is that E, N, and nu phase are all frequencies if you look at it in the right way. So indeed, this thing is quadratic in frequency, and it happens to have this frequency pulled out to the side, but it is nonetheless exactly what the doctor ordered. So, and let me not stop, I'm going to put something on top of there so I don't do it so many times, and go down here and get this one lined up as well. Okay, so the next stop is, well, what about momentum? Okay. Now, you got to realize that the 1900s was when Max Planck comes up with this as a crazy hypothesis, and then he says, "Boy, I was really crazy. I'm going to get. People are going to just tell I'm a crackpot and I'm out of business now." And maybe he would have been right if he had just stopped then, but he didn't. And Einstein kind of picked up where he left off. Momentum is a whole different story. Okay. It's got the hyperbolic sign. That's what we're getting here, if we put the exact thing in, okay? And then we got to do 1 over beta inverse squared. Well, that's nothing but beta over square root of 1 minus beta squared. That's the old-fashioned notation right there. And there it is. That's de Broglie's idea. Now you got to realize 1900 to 1921 is 21 years. That's a hell of a long time separating these two. Okay? It didn't take us 21 years to do it. It may have seemed like it was 21 years as we're sitting here watching this, but it's been about 21 minutes, right? So that's what's so cool about, I think, this way of looking at things with waves. And it's not a lucky coincidence. It's what waves do. It's a wave conspiracy. And I'd say it's an expensive trick. They paid me quite a bit to do this. Okay? Yeah. State money, right. Well spent. Okay. Now, all of this stuff is true here. Well, the only person smiling on this thing is the guy that comes along 21 years later, and that's Mr. Louis de Broglie. Okay, we're very grateful for that. But it's a while before Schrodinger gets into the act and starts to make wave equations based on, and he's only looking at the first couple of pixels on this hyperbola right here. And that's a parabola, and that's our good old-fashioned Hamiltonian, p squared over 2m. That's what this is. So you've got to really stretch the scale on this thing and close in on it this way to get this. So if you're going to play with this thing, most of the time, and this is what you see right away, is the e squared is this thing right here, and that's m squared squared plus 1 plus sine squared. I'm just writing it out in square functions. So I get the actual p squared to show here, plus this constant, which we throw away. Okay? All of this enormous frequency, if you're talking about an electron that's got, a couple of eV in some experiment around the lab here, you got to realize that the electron has 10 to the 24th hertz right here, just one electron. So the mc squared is just huge. How can we throw something so huge away? Well, very easily, because all we're interested in our experiments is the differences in energy. We don't actually measure directly energy. We're interested in the beats between levels, not the actual values of those. We've made that point with our two-level things, right? That's what you see in the beats, the differences you see. So, in the differences, the mc squared cancels out. You can throw it away. That's your gauge, so to speak. Okay? But if you're really going to play with having light make matter and back matter coming out of light colliding, or matter colliding giving light, the pair production, pair annihilation is the most elementary process, then you got to bring this guy back and start using this guy. So Schrodinger equation becomes a Klein-Gordon equation when you take this into account. Okay. And Niels Bohr then starts to use that, and that's where quantum mechanics really made its money, is through Bohr's models. Okay. Now the other thing that's here, and we're not mentioning that, and I'm very much remiss in not having figured much out about it, but this is all stuff with phasors that go clockwise. There's a whole nother hyperbola down here where they go anti-clockwise. That's the stuff that goes backwards in time, so to speak. So there is that to worry about. We're not going to do that very soon. I hope to do it soon, but it's one of those things that keeps going tomorrow. Right. Okay, so we've been remiss in keeping all of this stuff going on the table. Anyway, here is where you get to actually see, and that's kind of the punchline to this derivation. I mean, we basically derived the basic pieces of the quantum mechanical quantum matter, the very fundamental parts of it that, well, you eventually make the equations that you learn in quantum mechanics. So this table right here that has the Lorentz contraction, the Einstein dilation, we've been looking at in the last lecture, and then this one that's linear in the rapidity or the stellar aberration angle, the hyperbolic sign, that's the past-future asymmetry. So one of the things you notice by looking at this is that that infinitely fast phase thing, it goes up linearly, while the motion from going to some higher speed from the bottom of this hyperbola, you see, I can go a long distance here. I mean, quarter the speed of light, you know, is kind of out here where I start to see, my gosh, I have something here that's quadratic. But this, from here, it's constant, you see. So the effects that we talk about in relativity, second order effects, they're not noticeable in most of the classical mechanics we do, where we keep everything under an electron volt or so in energy. But eventually, it too has to. This one's linear. These two right here are, for the most part, second order Doppler shifts. That's really what it's going down to. But here, you see what's going to happen, and we can see this from the geometry pretty easily, especially when we start using the sigma angle. It turns out to be the polar angle of the Lagrangian, and it's sitting in this graph right here. The Hamiltonian, very obviously sitting there as a hyperbolic cosine. So this guy right here that has a hyperbolic cosine, if you plot that correctly and turn it over, you've got the St. Louis arch, right? We're talking about catenary, right? At least for a while, it's really a hyperbola, which is where the catenary comes from. So here's the Hamiltonian taking the place of time dilation. Here's the Lagrangian, as we're going to show, taking the place of the contraction, that miraculous thing that waves do. It's a second order Doppler squeezing. Well, this is the thing that's keeping track of that. Then the inverse of this guy is a de Broglie, and then there's the phase velocity versus the group velocity. So remember, on both of these tables, they're identical except for their physics. Everything on this side is inverse of the corresponding position here. This is inverse of that, and this inverse of that, and this inverse of that. So it's a highly inbred theory. It's got all of these things that get used over and over again, which can be very confusing. But here we try to separate that. Okay, now, what about matter? How many kinds of matter? It seems that we sort of be a little blasé about this particular constant here. Rest mass has got something in it really vibrating fast, and that thing right there has got even more vibration as you pick up your momentum. So the question is, as I ask, what's the matter with mass? This elephant is in the room, as elephants prone to do when something's weird happening that no one wants to talk about. Okay, he says he wants you to talk about it. He says, I matter. And the question is, how much kinds of matter are there? You see, what we're trying to do is get rid of some words that we think we know what the meaning is. We think we have a feeling for energy, but if you ask somebody that's giving a lecture on energy, like I did Art Husman one time, I said, how do you define energy? And he says, oh, well, it's just a measure of how much work you do. And I says, well, how do you find work? And you said, well, that's energy, I guess. So you're around in a circle with, you know, a word that you're supposed to be used to, but he realized, that's something we should need. Well, what we're saying here, that's inverse time, with something in there to make it the joule unit that you're used to. Okay, momentum, sort of inverse space, but we got to talk about this one. This one has a little bit more structure, and then of course we feel we're pretty confident about what velocity is, but it's going to turn out to be a derivative. In fact, you can see that on the graph that we've got here, in that if this is a plot of the energy dispersion, the tangent to that line right there, the slope of that thing is the group velocity. And the group velocity is sitting right in this territory here. Okay. So that distance here is the group velocity. We haven't written that in there, but there's a hyperbolic tangent from here to there that's written very clearly in this, in the let's go with us, what I handed you today. Actually, come to think of it, I did not have that in notation. That's something you're going to put on there. But the basic idea then is, here's one kind of mass that very famous kind of mass, that is, if you take that enormous frequency, okay, that you have, say for an electron, 10 to the 24th or so per second, and you put here an h bar on it. Now the h bar it is in our units just around 10 to the 30 minus 34 joule seconds. So that, you know, tames this down a little bit. But you've got this huge number in the denominator. Okay, so you've got a small number here, a pretty large number here maybe, depends on your mass, but then another large number in the denominator, so that makes the actual rest mass of this box of light, say it's in a cavity or it's in the waveguide moving along, you get a very tiny mass for a box of light, 600 terahertz, cranked up as much as you could crank a laser. You really are in the neighborhood of 10 to the minus 48 or 10 to the minus 45 kilograms. That's pretty small. Not something you're going to put on a scale and weigh right off the bat. But we all knew from Einstein's theory that if you put energy into something, that it's got to have extra matter. This is showing you how that happens. Okay, you've been there and it's bouncing around, you start to accelerate. It's going to be a little bit, 10 to the minus 44%. Less easy to accelerate that cavity. But the mass that you're talking about is so small compared to the actual Limvar steel that's holding that way, right? So we would never claim to be able to measure that any way we know now. Now you make things very small, and then nano, and beyond, it starts to actually play with you. But there's a thing called momentum mass. That is definitely part of any relativity course. And so what I'm going to do here to get that is I'm going to say, all right, I've got a new formula for momentum here. It's not mv squared or p squared over 2m anymore. That's 200, 200, but this one is mv or p. And I'm putting a c on it right there to get rid of this so this is linear, you see. That is the velocity, that's the group velocity. We're going to take the group velocity, which is the slope of that tangent to the hyperbolic course. We're going to use these new as of 1900s, 1921 formulas, and we're going to stick them in our definition of momentum. Okay? That is, that momentum would be a velocity times a mass. Okay? So I'm looking here just at the mass. I'm going to divide the velocity into the p. But I'm going to use these new guys, all right? Well, hyperbolic sine, this is hyperbolic sine over cosine. When you get done doing that, you see very quickly that you're going to be getting this very famous formula for momentum mass, which is just the hyperbolic cosine, Okay? So this hyperbolic sine that lives in this thing cancels this sign, but I have a 1 over cosine now. That comes up on the numerator, gives me that. Okay, is that clear? So that one's pretty easy to sort of psych out. That's just getting a feeling for what these quantities are. What you're seeing is that the idea of mass is very fungible. Okay, now the limiting cases, as you go towards C, is the rest mass, which does not change. That's the bottom of the hyperbola does not change as you accelerate past it. You've got this e to the rho as the main part of the hyperbolic cosine, so it goes up exponentially. And this is a lesson here. Most of what's going on in this business is exponential. Okay, all of the crazy things that are going on way out in space. Most everything is happening exponentially. This is just the beginning of that. But as you approach C, the momentum mass becomes the rest mass. And we don't talk about different kinds of mass in classical physics. Here you start to do that. Okay? Well, how about Newton's idea of mass? This is Galileo's. What about Newton's idea of mass? Okay, the idea of the ratio of a force to an acceleration. Well, the whole idea of the acceleration being a rate of change of velocity. Okay, or basically what we're doing here is we're going to take the derivative of p over the derivative of u, and see how that relates. Okay, so typical dp here, if I use the p that I have there, I take the derivative of that, and I get a hyperbolic cosine from a hyperbolic sine, and then this guy right here is the derivative of the hyperbolic tangent, that's sec squared. Put those two together, okay, in a dp over du, you get this. Okay, well, that's kind of neat, because this is a hyperbolic, inverse hyperbolic cosine, so it's two of those factors are going to come up here. You get this weird thing. Instead of the first power, it's the third power. That's called effective mass. Okay? Well, that's kind of neat. This one's going to go up as a triple product of the exponential. But for low speed, it's going to come back and be rest mass. Okay, so rest mass is what you'd expect you should get from all of these analyses. Now here's a more common difference. This is the one you use in band theory. The effective mass is just h bar dk, it's change in momentum over change in the group velocity, that is the classical velocity. But we use our new d omega dk here, and then we've got a dk here, so I bring that down as a derivative. Okay, that makes a second derivative of the frequency, the dispersion function, to be more precise. And that means in band theory, you're going to be looking for this, if you were talking about effective mass, in a definition of effective mass that you should be using. So I've seen it used completely differently in many of the talks that have come by here. But in any case, you get the same thing. You get an inverse 3/2 power of 1 minus the relativity parameter. That's the old-fashioned formula. And this is the simple formula. And it's the exact thing. There's no approximations here. So basically what you're looking at a dispersion curve, and you're saying how easy, how malleable to change in velocity are the waves that are on this curve. And you can see very quickly that we're talking about a second derivative of this thing. We start out, that's the minimum right there. That's the rest mass. But as you go out here, the circle of curvature, okay, for this thing gets bigger and bigger. The radius gets bigger and bigger. It gets straighter and straighter. It's approaching an asymptote, this hyperbola here. It's approaching a straight line. And the smaller the rest mass, the quicker it gets there. But anyway, what you're getting to the point, you see, where the effective mass goes to infinity. So that is, I think, important to notice about, that's what waves do. This hyperbolic dispersion gets very short. Now, light itself has an infinite effective mass. That is, it's on the asymptote here, or on any part of the light cone that you want to look at. And that means that it is not able to accelerate. It's going C and it isn't going to go anywhere else. That's our basic axiom, is that C is not going to change for a single CW. It's when you get two of them together that you get to play all the games that mass does, and then some. So this is getting us pretty much here. Now, Newton complained about his corpuscles of light. That's his whole book on optics is about light being corpuscles, that is particles. And he said that they have fits, and that's what they have when they interfere and make weird patterns that he could see. I mean, if you look carefully just at light onto a shiny piece of bronze or something, you can begin to see that. A sort of a speckly thing going on. He says it's crazy, it's absolutely crazy. But all of this, here's the photons thing, a gamma rest mass. Okay, no, it does no gap. There is no gap, MC squared gap, for this thing if it's a single CW. Okay, so that is absolutely zero. Okay, the momentum mass, you can write that very nicely. P over C, that's H bar K over C, or else H nu, frequency of the light, divided by C squared. Okay, and you can see here that we have once again, the denominator, large number, okay, and then a small number sitting here fighting that, or I should not fighting, going along with it, and then nu could possibly be a large number, okay. So this one is an actual formula we can use, okay. But what's the effective mass? Okay, effective mass is just infinite. That's light, single light by itself, not able to make a dispersion function. It's just a straight line in omega k space. And in space-time as well. Okay, typical momentum, 10 to the minus 36 momentum mass, 10 to the minus 36 kilograms for 600 terahertz. And I haven't said how much of it you're getting. This thing you multiply by quanta. Okay, now the relations that we may have time to look at just really briefly, and this is where the Lagrangian comes in. Lagrangian as a derivative of this thing we call phase, and there's the phase the way we've written it for just doing wave mechanics here. Now we're going to be writing it out using all this new stuff, or this new connections, okay, so that we can get both momentum and energy in nice formulas that we can make sense of, and that is a number of things that we've talked about in this class, like the Legendre transformation. Okay, here it is, Px dot, that's this guy right here, okay, minus the energy, that's the Hamiltonian, that's our Lagrangian, it's a derivative of phase. Locally, with the mass, and now as you see it go by, you may see a different derivative of it, and that'll be the Hamiltonian, roughly speaking. So one of them's local, the other one's global, so to speak. And also one of them is on the diagram just as a circle, and the other one is a hyperbola. So we go ahead and work all that out, compare the Lagrangian, that's what comes out of this, very, very nicely. The Lagrangian is the thing that was called the Lorentz contraction factor. This time it's got an MC squared. So the hyperbolic secant that lives on this circle. There's the Lagrangian circle right there. Okay, and you see the Lagrangian circle has the same curvature, but with a minus sign because it's pointing downward, as the hyperbola in this neighborhood. Okay, so they're both p squared over 2m, that's what the Hamiltonian would be, or 1/2 mv squared, group velocity squared, that's what you'd be writing for this with a minus sign. So that's a key thing to note about these functions. Okay, that hyperbolic secant is definitely part of the story on these, in this geometry. Okay, so let's see if there's anything else I can mention here. This is just working out the Hamiltonian again from the hyperbolic cosine, and this one from the hyperbolic secant. Okay, And this one, this is kind of interesting. This is the Lagrangian giving mc squared times the cosine of sigma. Okay, the cosine of sigma is the same as the sec of rho. Okay, remember the way these things are situated in this table, the secant right here, and the cosine right here. Secant of the rapidity, the cosine of the stellar aberration angle. The waveguide k-vectors, a polar angle is what it really is. So all of that is kind of shown on this graph right here, and I'm going to jump ahead on this one to that point where we can just, for sake of argument here, go ahead, and this is always a computer that gives me a headache when it comes to jumping to a site on the web, but let's just give it one more chance where we make nasty names about it. There it does its thing again. I've got to figure out a way to get around that.
We'll need to quit Firefox completely.
Yeah, that's kind of what it's asking me to do. And I have done it. So let's go back here and see if it'll go this time. No. Well, we're going to have to fix that bug. That's really nasty. But let's go over here and see if this guy will bring us up. And there we are. Okay, so this is this graph. I'm going to swell it up here. You do that just by working a little mouse wheel. What this is letting you do, of course, and if you click and drag, you can put all of the other side of quantum mechanics, which is the stuff that's going back in time, the antimatter, out of sight, out of mind. But this sort of geometry is just copied down below. And that, and I'm going to try to get this one back from the dead, because I want to show where all of this is. Okay, the basic idea that's not shown here, and you can see it at the bottom of this screen, is that Lagrangian, it is the sec, hyperbolic sec, is minus mc squared. So it really starts at the bottom here and then goes up with a parabola mv squared over 2. Mu is our group velocity. So here is the group velocity. Here it is right here. That's the hyperbolic tangent times the b. Now we really need to scale to give the right units. And then this one is that same b times the hyperbolic secant. So that's the Lagrangian right there. There's the Hamiltonian right there. That's the hyperbolic cosine that goes up and meets right here. This is all hyperbolic cosine from there to there. That meets the momentum, which is the hyperbolic sine. So we're just repeating the things that we have right here. That's the momentum. And there's the Hamiltonian being a function of momentum without the blessings of the Pope and the canonical friends. Right? This is why you really have to make something that is going to get infinitely large on this hyperbola with an infinitely large momentum as to being different from describing it as you would in high energy physics by something that never can get past the speed of light. The group velocity is ending right there at c. Okay? And it's this function that you see at the bottom of this still here. We don't have it quite in place, I don't think, on there. But anyway, as I mentioned already, might as well do it again now that you see a little bit more what this is. As I work myself off into the distance, you can see de Broglie wavelength getting really short. And, damn it, I always forget to turn off the swindlers. Okay, In any case, what you're noticing is we're coming down the Lagrangian here, approaching the speed of light, and the Lagrangian is this distance right here. So it gets, for high energy, it gets kind of small. It gets to be a small number, whereas the Hamiltonian is taken off. But you see, high energy physicists are all within a pixel of this point, and us, the molecular, atomic, and optical physicists, we're within a pixel of that point, right? So we use Hamiltonians very happily. Hamiltonian is a reasonable thing, and most of the time we subtract off MC squared, so that's our Hamiltonian, right? We just put this thing right at 0. The trouble is when you do that, the group velocity becomes faster instead of slower than the phase velocity, so don't do it if you're playing wave mechanics. You need that MC squared. And even when living in this neighborhood here. Okay. Well, anyway, the Minkowski graph, of course, covers the whole per space-time. We've only shown one little piece of it right here, and you can easily adjust that by playing with the controls to see how it affects things that are outside of there. I don't think there's much else I need to describe except that the stellar aberration angle, that's this thing right here that we've drawn in orange on the board over there. You can see it's the lower edge of the Occam sword, okay? And it's the K vector. The K vector ends right there. As you go faster and faster, the components of the K vector perpendicular to your motion do not change. But boy, this one sure does, and it starts to become very high frequency. As I said, as the stars move in front of you, look out, that light's bad. Light's got a lot of energy. Okay, I think probably the best thing here is to stop. There's a whole other lecture about how transitions occur, how Feynman diagrams work. You're absolutely welcome to, look at that and come and ask me questions about it. I'll be happy to talk about this stuff, as you probably already have seen. In any case, thanks for your attention this whole semester, and I hope that some of this will catch you. Okay. Any questions? We have, certainly you might want to just stay around and ask them privately, but if you want to do it globally, you're welcome to at this point. You can see, probably have the same feelings probably that Stephen Chu had.